Okay, so today our topic is comparative effectiveness of observational studies. And in particularly when I talk about propensity score analysis. So I'm going to talk a little bit about study designs and then some of the issues in doing research, particularly looking at selection bias. And then we'll talk about propensity scores and sort of two different methods, propensity score matching, and then inverse probability weighting. So as probably everyone knows, a randomized clinical trial is really the gold standard of research designs. And of course, the reason for that is because the randomization process at least hopefully equalizes potential confounders in the treatment groups that you're looking at. Let me just say that it works almost all the time if you have sufficient numbers. If you have small study, then it may not actually work. And in fact, I am involved in a study where that actually was the case. It was a pilot study, and there were only 20 patients in each treatment group, but they were randomized to the treatment group. And it turned out that those in the drug of interest were actually more ill than the patients who were in the placebo group. But that can happen when you have a small sample size. So just kind of be aware of that randomization might be an issue if you have a small number of patients in your study. So a randomized trial is the best method for establishing causality. However, there are a couple of downsides to it. It can be very expensive to do a randomized trial. And then there's an argument that you have limited data. That is, you don't have real life, or you don't have real life data. The other type of studies, observational studies, where they're not randomized to treatment groups. Some positives about that is, of course, that the data may already exist. And typically, if that's the case, you can usually get more information on patients than you can in a randomized trial. However, the main downside of observational studies is that you have the potential for selection bias, confounding, so that you can't really make a clear-cut decision about whether your treatment worked or not. So there's different ways of trying to reduce selection bias. One of them is that you can match by covariates, and primarily the ones that are used would be age, race, and sex. However, if you're going to do this, then only a few of these are really realistic, because if you try to match by age and race and sex, all three of them, then you're going to potentially have some rather small cells in your design. And so if you have a lot of categorical variables, this is going to be the case. And then with continuous variables, like for age, how close are you going to match within 2 years or 5 years or 10 years? So that's one way that selection bias is hopefully overcome. Another way that's a lot easier is just to do regression covariate adjustment. That is, all the covariates that you have measured, then just put those in a regression equation, comparing the treatment group with the placebo group or the control group. The downside here and we'll talk about another one, major one later on, but there might be a limited number of variables that you have available. And this also could be dependent on the sample size. So one of the ways, a common way that is used is to use propensity scores. And there's two different methods of using propensity scores. One is matching by propensity score, and the other is inverse probability weighting. And so we'll look at each of those and look at the differences between them. So the idea of a propensity score is it's the propensity to be in one treatment group or another, where group assignment could be assigned or randomized. But for whatever reason, whether it's maybe ethical or just impractical to randomize a particular outcome, you wouldn't be able to actually randomize. And also you don't use propensity scores to assign a comorbidity or a risk factor like diabetes, because they either have diabetes or don't. That's maybe one of the variables you use to identify treatment group. But it's the idea here that your propensity score is the propensity to be in one treatment group or another. And so what we're going to do is we're going to do a logistic regression where treatment group is the outcome. And so we'll talk about treatment A or treatment B here. And so we're going to use demographic and clinical variables as predictors of the group. And you'll use as many as you have available to do that. The one variable that you can't use or shouldn't use anyway is the outcome of interest. So for example, if your outcome is survival, then you can't use whether they survived or not as a prediction of which treatment group they're assigned to. And so the use of propensity score here is to have a study that is what we call quasi-randomized. That is, it is not true randomization, but it's can be pretty close to it because we've identified patients that are similar based on their demographic and clinical variables. So as I mentioned, we're going to solve a logistic regression equation for each patient. And as you know, the logistic is the probability of an event divided by 1 minus the probability of the event, or the odds, we call the logit. And so we're just going to use a regular regression equation to come up with a probability of being in one group or the other. And so the probability is just the exponent of the logit of the exponent of your regression equation divided by 1 plus the exponent of the regression equation. And so if the probability of being in group A is P sub A and P sub B is the probability of being in group B, then the probability of the group being in group B is just 1 minus the probability of being in group A. So what is typically done then is we get a propensity score, and then we match a patient in A with a patient in the other treatment group with the same propensity score. Now, obviously, you're not going to get, or rarely do you get exactly the same propensity score. So the question comes, how close do the propensity scores need to be to match the patients? And so what we do then is we set a criteria, some criteria for a match. Are we going to match within 10 to the minus 4 decimal places or 10 to the minus 6? And so that's a decision that we need to make in calculating whether propensity scores are the same in one patient in one group and one patient in the other group. So here's an example. So I just, put in some numbers here. So in the very first row there, patients A and B, they're matched out to 8 decimal places. And then in the second row there, they're matched to 7 decimal places, and then 6, and so on, down to where they're matched within just 3 decimal places. And so what you will need to do is to set how close you want to match. And obviously, the closer the score between the 2 patients, the greater the match. However, it turns out that when you do propensity score matching, that some patients might not meet the matching criteria. And so it turns out in almost every study that you're going to have to, that you'll exclude about 30% of the patients because you can't get a match within the limits that or the criteria that you set. So that's one of the downsides of propensity score matching, is that you're going to have a certain percentage and even up to 30 or more % that aren't going to match. And as then it goes without saying, if you don't get a match, then those are not in those 30% are not going to be included in the analysis. So a way to get around that is to use inverse probability weighting. And in this case, the probability is the propensity score. And so essentially what we're going to do, I've kind of written this out in in a formal way here, but basically what we're going to do is take the inverse of the propensity score for each patient. And then for the patients in group A and the patients in group B, we're going to have a propensity score in a sense, but it's the inverse of the propensity score. And so in this case, then we can use everybody because in the patient sample that we're looking at, because everybody's going to have an IPW. And I just make a note here that if you just calculate the propensity score, that most statistical software, that's all you need to do, because they'll do the inverse probability weighting. So as I mentioned, in this case, we can use all patients because everybody has an inverse probability weighting. We can also censor the response data in this case, like if we were doing survival analysis. The one disadvantage, though, and this is also true of matching or doing covariate adjustment, if you have an unmeasured confounder, in other words, there's another variable that you haven't measured that affects the outcome of being in one treatment group or another, then you have a potential problem, obviously. Of course, the issue is you don't know whether you have an unmeasured confounder or not. I'm going to give an example where we can at least do a sensitivity analysis to get some idea of what it might take if we have an unmeasured confounder, what it might take to change the results. So I want to give an example here of a study that we did quite a while back. And so this is an intervention to improve neonatal outcomes. And so we have outcomes before the intervention, and then we have outcomes after the intervention. And the outcome here that they're interested in is birth weight. So obviously this is not a randomized trial because you're going to have different patients before and after. Although I guess it's possible you might have some that are the same from the pre and the post. So this is a diagram of the study. So pre-intervention is in the year 2004. And so you have a group of women who are giving birth before the intervention. The intervention occurs during 2005, and then we measure the outcome in women giving birth after the intervention in 2006. And so I have a tabulation of the sample size for years 2003 to 2006. And so the number pre-intervention in 2004 is 5,500 and some, and then after the intervention is 4,700 and some. So we have over 10,000 potential participants in the study, but of the 4,700 in the after intervention group, only 40% participated in the we have only 40% that actually participated in the intervention. So that leaves us with almost 1,900 for the study. And so what we're going to do then is because obviously this is not a randomized study, we're going to use propensity scores to match or to hopefully equalize patients pre-intervention and post-intervention. And so here's a list of the variables that are going to use to develop a propensity score. And you can see there's quite a few. And so this is one situation where you want to use as many variables as you can, because the idea here is to develop a propensity score based on as many covariates as you have. And so in this study, we have quite a few. So our criteria here is we're going to match at 1/10,000th or less. So in other words, if the propensity score has to be within 0.0001 or less. So it turns out that we have almost 3,500 pairs. And so when we match, we only get 68%. So 3,200 are discarded. So it turns out that we have 1,400 intervention pairs. Okay. So in other words, we have a patient in the before that's matched with a patient after the intervention. And it turns out that that's 41% of the number of pairs we started out with. And so here's an example of the matching. So in the very first row there, the very first patient in the post-intervention year 2006 is matched with a patient in the pre-intervention year 2004, and the difference in their propensity scores is really, really small. In fact, they're virtually the same. And as you go on down the list here, you can see that some of the propensity scores are still quite similar, although they're getting to be more and more different. You notice, though, that there's a number here that we can't use. So, for example, here's a matching pair, but the patient didn't participate in the intervention. So we can't use that patient. And then there's several here that we can't use because they end up either not participating or they're in the same group. And so you see that that's how we end up with fewer patients than we might when you do propensity score matching. So in terms of the analysis then, this is a pre-post design. We have matched pairs and our intervention or no intervention is the factor that we're interested in, the independent variable. And so obviously when you have a pre-post design, you have correlated data, even though they're different patients, because we've matched them, then the data is correlated. So here we're obviously what we're trying to do is simulate a randomized trial by balancing out confounding factors. Obviously, this is not perfect, but it's perhaps as close as we can get in a non-randomized study. So it's, as I mentioned, it's correlated data, and so that can be either continuous or binary. If it's continuous, we can just use a paired t-test. If it's a binary outcome, then we can use McNemer's test for correlated proportions. We can also use, if it's a continuous variable, the general linear model where we have repeated measures analysis of variance. And so we have the two time frames, the year 2004 and 2006. So here's what a t-test would look like comparing year 6 with year 4. And so we have 1,423 matched pairs, and then the particular interest or statistic of interest here is the difference between the two. So we see that the difference between the pre-intervention, the post-intervention is 61 grams. So whatever the intervention was, we can say that there's evidence that it increased birth weight by 61 grams. And of course, with a large number here, that's going to be statistically significant. So we can also, as I mentioned, do this as a repeated measures analysis of variance. So if we structure our data as what we call long data, so in this case, you have two IDs, number one in year 4 and one in year 6. So there's actually two different individuals there, but they've been matched. So their ID would be the same. And then we have the birth weight for each. And then we can do just a regular regression. And in this case, we tell it that there's a cluster as ID because we have matched pairs. And so you can see that in this case, we get the same result as we did just doing a t-test where there's a 61 gram difference in year 6 after the intervention. So I want to give you then an example of a study that we did a while back where we looked at the comparative effectiveness of revascularization strategies. In other words, basically what we're going to do is compare PCI, percutaneous coronary intervention, versus CABG, coronary artery bypass, with respect to survival. And so what this involves was matching two different databases, from the NCDR database and then the Society of Thoracic Surgeons database. And this was for the years 2004 through 2008. And then, so the outcomes that we're going to compare, survival, we're going to use inverse probability weighting to reduce potential treatment selection bias, because obviously this is really two different populations of patients. And so we're going to need to do, and it's obviously not randomized. So we're going to need to do something to reduce treatment. So we have quite a large number of patients in the databases. And so it turns out that after going through the databases and applying exclusion criteria, that we have 103,000 some undergoing PCI and 86,000 undergoing CABG that were included in the analysis. So obviously the patient characteristics could be really different between these two populations. And so what we're going to do then is to compute propensity scores and then use the inverse of that to get inverse probability weighting. And these are just excerpted from the studies or from the papers methods section. So when you do IPW, inverse probability weighting, one of the things that is necessary is that the propensity scores between the two groups have sufficient overlap to be able for IPW to work. And so this is a plot of the propensity scores for the two groups, and you can see that in this case, there's a fair amount of overlap. And so why do we need this? Well, we need to have the overlap so that we can have a propensity for being in one and a propensity for being in the other that has the possibility of being from the same, in the same, has possibility of being in the same treatment group. So if you have something that looks like this in terms of their distributions, then IPW is not going to work, because in this case, the inverse probability actually defines the groups. So that's why we have to have an overlap in the distribution of the propensity scores. And so here's our table 1 that has the baseline characteristics of the patients. And so these are going to be the variables in the left-hand column that we're going to use to calculate the propensity score, and thus the IPW. And so if you just compared these straight up, you can see, or without any adjustment, you can see that there's a big difference. Although because of the sample size, a lot of these differences are actually quite small. It probably would have been better had we used standardized differences, but nevertheless, this illustrates the idea of then using the inverse probability weighting. So on the right-hand columns, you can see that when we've done the adjustment with the IPW, that all of the differences are no longer statistically significant, and that we've what the IPW has done has made the distribution of those characteristics pretty much the same in each group. And so this nicely illustrates what IPW does, and we're able to use all of the patients in the in the study. So it would be, if we did matching, we would get probably quite a few who wouldn't actually match. But by using IPW, then we can use everyone that in our sample. So this is the results of the outcome of survival. And so you can see that the survival curves of the two intersect. And so I use Cox proportional hazard for this. And as you know, that's when you have survival functions crossing like that, we don't have proportional hazard. So that's something that we also had to adjust for. But if you look at the bottom row, the relative risk with cabbage row over the time frame there, you can see what's happening, that at 30 days, the risk with cabbage is 72% higher than it is with PCI. However, at 1 year after their revascularization, you can see that it's pretty much equal. And then at 2 years and following, then the relative risk with cabbage for survival is about 20% greater than it is for PCI. So basically the conclusion here is that we have an initial benefit of PCI, but a long-term benefit of cabbage. But this was a study that where we used the IPW to match or to not match, but to more or less equalize the two groups with respect to baseline characteristics. So another thing that we did in this study, which I'm not sure I've seen it in others studies that have used propensity scores, is that we looked at the potential effect of a unmeasured confounding factor. And so this is, obviously going to be a simulation. But what we're looking at here is how powerful a single covariate that's confounding the results would have to be to account for the advantage of cabbage over PCI. And so what we're doing here, on the horizontal axis is the prevalence of the confounder in the PCI group. And then the colored lines then represent the prevalence of the confounder in the cabbage group. And so looking at this as an example here, if the confounder was present in 10% of the cabbage patients, but in 35% of the patients in the PCI group, and if it increased the risk of death by a factor of 2, then that confounder alone could account for the observed difference in mortality between the study groups. Now, I say this is obviously just simulation. You don't really know whether you have an unmeasured confounder in your study, or there's a variable you didn't measure that would have really affected the results. But the simulation here is that if you have different prevalences of the confounder in each group, what would the hazard ratio be that would change the outcome or the results of the analysis. So several things here that I want to go over. So the propensity score is a probability of assignment to a group A or B, and we get this probability from logistic regression equation, and we come up with what we call a pseudo-randomized study. And so as I talked about before, the probability is obtained from doing a logistic regression where the outcome is the logit of being in one group or the other. And so you might say, well, okay, what if we have more than 2 study groups? Well, we can do the same thing, although it becomes a little more complicated by using multinomial logistic regression, where we have more than a dichotomous outcome. So in summary, then the propensity score matching, we match by the closest propensity scores, and we match within a specified precision. And as we mentioned, about a third of the sample won't match. However, we can overcome that by using IPW, inverse probability weighting. And so what we do in the regression analysis, we specify the weights. And in this case, all patients in the sample are available for the analysis. And we don't, and I've seen this done, although you don't really need to do it. I'm not quite sure how that affects the results, but if you're using IPW, then you don't really need to include the covariates along with the IPW in the analysis, because that's what you've used. You've used those covariates to compute the IPW. So in case you see that, and I say I'm not quite sure how that affects the results or the outcomes, but the IPW is sufficient to include in the comparison. So I have some references here. A study that appeared in the New England Journal, another study about how you use and the limits of propensity scores. And of course, there's always those who really don't think propensity score matching is very useful. So there's an article there about not why propensity scores should not be used for matching. So, and also let me just say that most of the major statistical software, SAS, Stata, and of course you can do it in R as well, will do propensity score matching, either the IPW version or the matching. So I want to thank you for your time and attention to this. It's not as long, but there's a lot to think about when you have non-randomized studies. And so I can take a few minutes here if anybody has any questions. I guess you use the Q&A to do that. Or if not, just email me some questions that you have at my email address. So I'll stay on, since we have some time left over, I'll stay on for a few minutes if anybody has any questions, or if you want me to go back over a particular slide, I can do that as well. Otherwise, thank you for coming today, and we'll look at next month, April. We'll look at Bayesian statistics. Let's see. Okay, let me see here. Oh, okay. You're welcome.